Good evening. For those of you who don't know me, I'm Tim O'Shea, Principal and Vice Chancellor, and it's a great pleasure to introduce Leonid Libkin for his inaugural lecture. It's really good to see such an audience here, but can I express particular pleasure that the Consul General of Russia is with us this evening. Very, very good to see you here. And the partnership between the University and Russia, as I was just discussing with the Consul General, develops in so many ways through high-quality staff, high-quality students, and obviously our new Ruski Mir Princess Dashkova Center. We are very, very privileged indeed to have Leonid Libkin amongst us. He's a world-class researcher in both logic and databases. He has answered some of the most challenging open problems in database theory about practical query languages. He has invented a new approach to database design, and he has produced a comprehensive body of work that unifies finite model theory, automata, and XML data. He holds a PhD from Penn. He was appointed to a full professorship at Toronto in 2004, experience in Bell Labs, experience at INRIA, and here his awards include the Marie Curie Chair Award from the European Union, the first ever to a Scottish institution and the first for a computer scientist. He has 4 Best Paper Awards at leading database conferences, about 150 papers, and 4 textbooks and monographs. Since coming to Scotland, he has developed research interests on data integration and exchange, XML and graph databases, and he has established strong research ties with Russia and with South America. And he visits Russia in the summer and South America in the winter. Sort of like a migrating bird, obviously a rational migrating bird. He's also developed a nose for the finest malt whiskies. So now it's a great pleasure to ask Leonid to speak to the title, Separating Possible from Impossible, or Why Practical Computing Needs a Theory. Please welcome him.
Okay, thank you very much for the introduction. I hope you can all hear me. So the title is Separating from Possible from Impossible, or Why Practical Computing Needs Theory. And I'll start by saying a few words of what we think of practical computing, what practical computing is. So if you ask people what they think of that, I imagine most people would think of a picture like this. That's an actual picture of some supercomputer doing lots of computation. Or they would think of the use of computer that now follows us from the very first days of our lives, sometimes even before we can say a single word, and continues to follow us until the very last days of our lives, and quite often even beyond that, right? So this is, so computers surround us at all times. And, it's when we open newspapers or listen to the news, you can hear all items about computing in real life. So most aspects of computing that you would hear about, so if you are not a computing professional, would be things like processing very large volumes of data, right? So, whenever you call any company that's supposed to have information about hundreds of thousands of people, if not millions of people, they find you immediately when you give them one number, right? So you sort of know this type of applications. Numerical computation and things like weather forecasting. Of course, we all use computer networks all the time. And on everyday basis, we deal with things such as security and cryptography, say every time you make a purchase on a website, and so on and so forth, right? But of course, what we do here, we do computing research. And despite all these images that I showed you, so if you talk about computing research, at least the way it looks to an outside observer might be quite different. So in particular, if you come to this very building and go to the 5th floor where I sit, and when quite a few people in this audience sit, then you're not going to see like any of the pictures I showed you before. Most likely, you will see something like this. Right? And and actually it's probably not projecting quite well, but we love Blackboard so much that the background of my presentation that I did in Keynote is actually called Blackboard. So I'm trying to emulate Blackboard and chalk, right? So now, but then the question is that what is that we are doing and how it relates to other things that we're all that you may think about if you are talking about practical computing. So in particular, what would be the connection between things that you would think about and things that make us happy as researchers, which is, I just took a page that from my book, actually, with a proof that I'm particularly happy about, but it's just a random page. And so, but this on the right is, is what we do, on the 5th floor over here, that type of things, right? So to answer this question and to hopefully establish some connection, we have to say what we mean by us. So who is us? So us is theoretical computer scientists, right? So that describes absolute majority of people on the 5th floor of this building. And what do theoreticians do? Well, theoreticians do the same thing as mathematicians. Theoreticians prove theorems, right? So, but why do they prove theorems? So what's the point of proving theorems when we're dealing with computing? And so what does it have to do with computing as we know it? So that's what I will try to explain. At least not everything, of course, it would be absolutely impossible. Just some aspects of it, in particular aspects of it that are close to my own work. So what is it that we prove? Well, obviously we prove many things, but the result that we particularly like is, and the results that I will concentrate on today, is results of the following kind, that some tasks cannot be done by computers. Sometimes they cannot be done by computers at all, but sometimes they cannot be done by computers if we impose specific restrictions on resources, saying it has to be done in a given time or using a given amount of memory, that sort of usual restrictions on the typical, on typical computing requirements. So that's the kind of tasks that, the kind of problems that I would want to talk about. And, but the first question is, and this, you hear occasionally that question when you try to explain what you are doing to other people, then they say, well, should we really care about that? Because won't computers be able to do all we want sometime fairly soon? So there is definitely this tendency to think that, wait a few more years and there will be yet another better processor and we'll just do whatever we want because it will be so fast. So in generally, everybody knows, or almost everybody knows about Moore's law, right? That says that capabilities of computing devices, such as processing speed and memory, double roughly every 2 years, right? Maybe 18 months, every 2 years. There are limits on this doubling, and the limits are imposed by physics. But the trend will probably continue for another decade, maybe for another couple of decades. So, and we know that what was completely unsolvable 2 decades ago, now we can just do it routinely on laptops that we carry with us and are not even viewed as very powerful laptops. So the question, should we even care about the fact that some problems are not solvable now? Maybe we should just sit down and wait and until Moore's law, and in particular companies such as Intel, IBM, Apple, and others will just do the job and these more powerful computers will do things. So the answer is no. Moore's law is not a universal cure, and I'll give a very simple example here. And this very simple example is tiles. So I'm talking about a tiling problem, and the problem is this. So we have a bunch of tiles, like of different colors, say red, blue, green, yellow, and so on. And we have some set of compatibility rules. So here, for example, we say that if you have a red tile, then on the right there has to be a blue tile. And on the right of a yellow tile, we have to have a green tile. On the top of the green, we have to have red, and so on. Right? So that's the compatibility rules. And then the question is, if you have a surface, can we tile that surface in a way that respects the compatibility rules? Right? So this is a computational problem, really. So what we have a bunch of tiles of different colors. And we have these compatibility rules, right, which are expressed here by pairs of tiles. This one says that it's OK to put gray on the right of blue. It's OK to put red on the right of green. And this one says it's OK to put gray on top of red, and so on and so forth. And so now we have questions. So first, I have some walls. I have a 3 by 4 meter wall, right? And the tiles are 10 centimeters. Can I tile that wall? Second question is somewhat general. Can I tile every wall? Right? Maybe this set of tiles is so great that I can always use it. Or can we tile some wall nicely, for example, so that the left side and the right side would match and the top and the bottom would match? Right? So now it turns out that the tiling your bathroom wall or whatever wall you have is a computationally infeasible problem. So the problem would be this: suppose we have numbers n and m, just say we have an n meter by m meter wall, right? Or n times the number of tiles in wall. And the problem is, can we tile a wall given the tiling system that we have? And it turns out that there is no chance to rely on Moore's law in this case, because if you increase the n and m by the size of just one single tile, then this will eat up all that all these companies, Intel, Apple, IBM, whatever, give us in 2 years. So this double increase will be eaten up by just increase by a single tile, right? So basically, by the time when physics stops Moore's law, what is going to happen in 10 years or 20 years, right? So we should be able to calculate how to tile the bathrooms in academics' flats. But obviously, you know, if some oligarch will come to us and say, can we tile a bathroom here in my flat nicely or in my mansion nicely, then that will have to wait. OK. And then there is something that, you know, we can refer to as philosophical tiling, when we have tiles but nothing to tile with them, right? So then we can have different questions, like, for example, are these tiles perfect? Can we tile every wall that we have? Or are they useful in some way? For example, can we tile some wall nicely in a way that sides match, left side the same as right side? And it turns out that these questions cannot be solved at all by computers, no matter how hard you try. Right? So these questions are completely unsolvable. So if you look at type of problems that we deal with, in general, you would expect that there is a dichotomy, that there is that problems could be either solvable or unsolvable. But what we see here is something different. So instead of the normal solvable and unsolvable dichotomy, we seem to have 4 different types of problems. So we have more possibilities. So one possibility is that we have a problem that's solvable and solvable efficiently. Right? So in some reasonable amount of time, we're going to get the answer from a computer program that is trying to solve the problem. So the second is that the problem is solvable not very efficiently, but if you throw in lots of resources at the problem, we can do it. Right? So the third is that the problem is solvable in principle. Right? So somehow theoretically, the problem is solvable. So if you have an absolutely humongous amount of resources, but not in real life. In real life, there's absolutely no way that you can build a powerful enough computer to solve it. And the fourth is the problems that are not solvable at all. Even if I manage to throw in all the resources, everything I have in the universe and more, I still cannot solve it. Right? So if you look at this in slightly more detail, so the problem solvable efficiently is really lots of problems that we deal with on everyday basis when we use computers. For example, database queries are such a problem. Finding routes in networks is such a problem when you send your message and it arrives at the other end in somebody's mailbox that has to find its way through the network. Lots of problems with cryptography. Lots of problems in software verification, hardware verification. And the list goes on and on and on. And basically, every computer science course that we teach here, right, you'll find lots of problems that belong to this category. So problems that are solvable with lots of resources, there are also plenty of them. For example, problem of resource allocation. You have several tasks. You have to allocate tasks to resources that in some way maximize some utility function, say a profit. Scheduling task, right? So we have courses to teach. We have professors. Professors have their requirements. We have to assign professors to courses. Well, that happens to be one of those tasks that actually is fairly hard to solve. But if you throw in lots of resources in it, then you can do it. Query optimization, not evaluating queries in databases, but optimizing the queries, taking one query and finding another equivalent one that is that will run much faster. So evaluating large queries, verification with large specifications, and again, the list goes on and on and on. So similarly, in pretty much every course, basic computer science course you can imagine, there will be lots of problems of this kind. And this is sort of what I would call the engineering, in the sense that you see the problem, you think hard, you find the solution. But you know that these problems are, in principle, solvable. But then we have the last 2 kinds of problems, and this is what I want to talk about. So here is a problem that's solvable in principle, but not with resources that we can possibly afford. So here I quote a famous example from a paper by Stockmeyer and Meyer from the 1970s. And the quote is, so basically what they have is the following. So look at the problem of checking validity of some logical formulas. So validity means that the formula is always true. Right? And the formulas are not very long, so they are less than 1,000 symbols. So they should not be viewed as terribly long. And now they say, suppose that we can build a special circuit that will just do nothing but solve the validity of these problems. And this circuit is the most optimal you can imagine. It cannot be better, because the gates in the circuit will be the size of protons, and the wires between them will be infinitely thin. Then guess what? That circuit will have to fill all the known universe, right? So you cannot. So this is a problem that in theory there is a solution to it, right? In practice, it's clear that we will never achieve that. Right? So we cannot waste this universe to solve that problem. And then there are problems not solvable at all, like the tiling problem, right? So I give you the tiles and I ask you, can you tile something with them nicely? Or is it true that you can tile, that this is a universal set of tiles that you can tile every wall you have? And there is simply no way that we can solve this problem using computers. Right? So what's the role of theory in that? So the role of theory here is that if you look at the engineering problems, in other words, solvable problems, then the role of theory in that is the same as the role of mathematics in natural sciences. But if you look at unsolvable, either completely or in this world problems, then in those cases we must prove statements that no matter how hard we try to solve a problem, we cannot. And now so the question is, why do we have to prove something? Well, we have to prove something because saying that no matter how hard we try assumes an infinite number of possibilities. We cannot just go and try and say, no, it didn't work. Try, no, it didn't work. Try, no, it didn't work, right? Even though, well, we teach courses, we quite often see that that's precisely the approach that many students take, but still, when we try to do it, we cannot, right? So, and this assumes an infinite number of possibilities. Okay? So, this is, one of the tasks that theoreticians do, but, how does it connect to practical computing? So basically, whenever we talk about theory and practice, we can talk about how theory connects to practice in theory and how theory connects in practice, right? So first, how theory connects to practice in theory. Well, we have this dialogue that here's a practitioner who says, look, there is a problem. I keep working on this problem. I'm thinking very hard, but something must be wrong with me. I just cannot solve it. Then theoretician thinks for a while and says, aha! It's not because you are stupid, but because no one can solve it. And here is the proof. I proved this for you, right? So this looks nice. In practice, it's not so rosy, and I will actually finish my talk with some thoughts on that. So it's usually not as bad. And so this is for the back row. It just says, you want proof, I'll give you proof. So it doesn't usually get to that, but sometimes it gets close. OK. So now, what's the proof? So why do we need proofs? What's the proof, and why do we need to prove things? So of course, at the end of this lecture, we will experience a different meaning of the word proof, and when drinks will be served. But I'm not talking about 0.5% of alcohol. So rather, I'm talking about rigorous argument establishing the truth of a statement. So in particular, the universal statements, the statements of the kind for all objects something is true, they tend to require proofs, right? Because we simply cannot do them by exhaustive search. We cannot say, oh, here is an object, right, that demonstrates that. We really have to go over all of them, and that requires proofs. And for the Russellians in this room, I have to say that, of course, all universal statements, including the one above, are false. So, but nonetheless, finding proof is the main activity in mathematics and theoretical computer science. So what I'll do now, I'll give you 3 examples that are connected to my own work and from the field that I like a lot, and this is the field of data management. So this is a field that we all use. We can hardly spend a day of our life these days without using databases. Most of the time unknowingly, sometimes knowingly. What we do pretty much every day, we generate a code in a language called SQL, which is the main language, the industry standard for accessing databases. So every time you purchase something on Amazon, whenever you search for, say, your favorite book or whatever item you purchase, right? So what it does, it actually generates a query in this language, sends it to a database, retrieves the data, and displays it to you in a nice shape. Every time you go and withdraw money from your account, there's a transaction running on a database that when you get the money, it has to go to the database that has data about your account, update your account balance, subtracting the amount of money that you withdrew. When you book your airline tickets, when you do pretty much everything, there is usually a database behind pretty much every computer application you have, right? So, and quite often when you fill out forms, what you do, you generate queries in this language. So behind the theory of that field is techniques from many other mathematical fields, including logic, algebra, combinatorics, automaton formal languages, algebraic geometry, information theorem probability, and so on and so forth. So how do databases look? So most of the time they look something like that. So we have tables, right? And so these tables have attribute names. So here's a table that stores employee IDs together with the name of the employee and the ID of the manager. And here's a second table that has an ID of an employee and a job title and a salary. Right, and so here, for example, says that the employee Smith has employee ID 123456. He is managed by an employee who has salary of who has ID 235711, and the name of that employee is Jones. Right. And the type of questions that we ask about the databases are this. So there are basically two main kinds of queries. So one is simply manipulating data. For example, find people who manage programmers. Right? So if you want to find people who manage programmers, what we do, we go back to this database and say, OK, so here's the job title of this employee 123456 as a programmer. Let's look up this guy over here. So his name is Smith. So here's his manager, 235711. 235711 is Jones. So we say, fine, Jones is managing programmers. Right? So we just manipulate data. Or say, find sales representatives who make over 50,000. Right? And the second kind is when we do both manipulation and some kind of counting with aggregation. So this is very, very, very common. So here's a typical query of that kind. Find the average salary of programmers. So what it tells you is that you have to go find all the programmers, get this big set of guys, right? Look at all their salaries and find the average. So basically you aggregate, right? You find these aggregates, right? So, and you find the sets and then you find some aggregate value over that set. Or find the total salary of all employees who are managed by Wood. And so these are the examples. And database systems are extremely good at evaluating these queries very, very fast. Right? So basically 40 years of research into databases query evaluation gives us now products that are extremely good at doing these things. But there are also other common queries that we may want to ask. For example, we may want to ask for all the people who work in the division that's managed by Wood. That is, they report to somebody who reports to somebody who reports to somebody who reports to somebody who eventually reports to Wood. But we have no idea how long this chain is. We may want to ask for average salary of such people. And it turns out that database systems are not good at all at evaluating such queries. And in fact, the standard languages that we teach in every introductory database course, in fact, just don't seem to be able to express such queries. Right? Now, when I say they don't seem to be able to express such queries, then there is a natural question, why is it that we even have limits on the expressiveness of queries? So why don't we let query languages express anything we want? So the key reason for that is that databases tend to be very, very large. So we usually, the way we deal with databases, we send a query to a database, right? So here's the database, and then we have a result. But database is extremely large. So if you don't have any control over our queries, then we may really have to wait for a long, long, long time, sometimes forever, to get the results. So databases are very good at evaluating queries efficiently, but to be very good at evaluating queries efficiently, they have to have very tight control over users' queries. And therefore, they have to settle for that for some limits in their expressive power. So in fact, the languages that they use, so essentially what they use logic. Right? So in particular, so if there is no counting, they basically use logic. So I'm not going to give the full, the proper logical notation, but I'll try to emulate it here with the text. So, here's an example of a query. Find people who are managed by someone who is managed by Wood. So the way I would say, give me all people X such that there exists a person Y, so that Y manages X and Wood manages Y. So I'll try to write it as a logical sentence. And query languages, real query languages we use on an everyday basis, they're effectively these logical sentences put in some special syntax for programming. Or like here I have a micromanaging CEO who wants to manage everyone. So I say, give me an X such that X is a CEO, and for all other people Y in the database, X manages Y. Right? So I just use logic for querying. So there's a standard query languages. They would appear in every textbook. As I said, most often in different syntax, but from the point of view of what they can express, they are the same. But then if you go, there are problematic queries. And problematic queries would be like, find all people in the division managed by Wood. Let's say this is a hierarchy of people, right? And so here is a guy, Wood, right? And there are people who report to him, and people who report to people who report to him, and people who report to people who report to people who report to him, and so on and so forth. And I don't know where it ends. And now suppose I just want to get all these people together. So it was recognized quite early that the standard languages that database people propose just don't seem to be able to do queries like that. And in fact, unnoticed by database people, this was formally proved in 1975 by Ron Fagan. So by the mid-1980s, the database people, having reproved that result or learned about it, basically all knew about it. And at that point, a decade later, they wanted to change the industry standard for the language to incorporate such queries. But there was a question, did they actually know what they wanted to know? Well, and the answer is not really, because real languages, such as this language SQL, which is the industry standard, they all use this counting. They all use this ability to get groups of people, for example, aggregate over them to do things like give me average salary of all the programmers, right? And Fagan's proof, which people were citing, explicitly disallowed even the simplest form of such counting. There was just no way to use that. And now the question is, what can we really say about real-life languages such as SQL, which turns out that most of the time unknowingly we use every day? So can SQL do such queries? So or do we need to change industry standards and add more features, as in fact happened with the 99 SQL ANSI standard? Right? So if we go to if you look at the theory of practical languages, then as I said, the problems about the power of SQL, of SQL, of this language, were open since mid-1980s. Basically, they were open since the time it was realized that there were those problems, right? And we had a research program that lasted almost a decade, from 1993 to 2001, and the goal was to answer those questions. And so what we did finally achieved by the end of the millennium, well, roughly 2000, 2001, is that we had all the answers that we wanted. So in fact, it turns out that we still cannot do those problematic queries, like find all people in the division managed by somebody, right? So, and even more, no amount of counting will ever help. You can throw in all the counting power that you have, all the aggregation power that you have. You can go way beyond what current languages let you do, and you still will not be able to do those queries. So in that sense, SQL 99 designers, the designers of the standard, were absolutely right in their decision to add those new features, because you could not have expressed those queries by any other means. You really had to add them explicitly to the language. So, and now the question is, why did it take so long, right? So I said it took 8 years. Well, when you start looking at problems like that, you don't start from nowhere. You don't say, oh, look, this is a cute problem, let me solve it, right? Let me sit down and solve it. So you have to develop tools to solve these problems. So in this case, there were actually 3 different sets of tools that had to be developed before a proper proof could be given. So the first tool was the notion of locality of logics, basically proper formulation of statements saying that what you can express in logic cannot see very far, right? So intuitive idea here would be that if I want to find something about, say, this guy in the middle, right? So I will not be able to go too far from this guy to know everything about how people relate to him, right? So I can only see a small portion of the hierarchy, and the portion could not be as big as the hierarchy itself. So that's the notion of locality, and so this is actually now used in quite a few other applications, not just in database theory. So then we had to develop a proper reformulation of SQL, because you don't start working with an actual description of the language as is given to you. You have to translate into something manageable that you can actually prove things about. So and finally, we had to develop the theory of logics with counting. And so with all these ingredients, we managed to give a proper proof of the result only in 2001. But did we cover all the practical features that the languages have, or is there something else? Well, the answer is not really, because practical languages operate with actual objects. They operate with things like numbers, strings, right? So they may ask for things like, give me all the managers whose last names start with a W, or pairs of employees who together make more than CEO, right? And so this would be the statements that you would actually find in real programming syntax for languages for using database. You would say that name is like W followed by, so this means anything. Or salary of 2 employees is greater than the salary of the CEO. So you can ask those things. And the question is, does the theory that we have, that we had built, apply to databases with such operations? So there are 2 answers to that. So first of all, there are easy languages. And what I mean by easy, we just take the languages that we had before, and we extend them with such operations. And then it turns out that nothing changes. Well, the results don't change. The proofs do. You still have to do it, right? But not in a terrible way. So you take something that's in the arsenal of most working mathematicians called Ramsey theory, you just mix it together with what you had, put it in the oven, wait an hour, and the proof is ready. So that's not very hard. So what turns out to be much harder is that there are different types of languages that also extend the semantics. And this type of languages are used in different applications, for example, geographical applications or spatial temporal applications, that things when I want to talk about geographical objects or how an object changes its position in time, right? Where comparing position of an object at one time with that position at another time. And when we throw those things in, it's a whole new world. Turns out that what we can say in the language depends very heavily on the properties of those arithmetic operations that people have studied, mathematicians have studied for decades, and in some cases for centuries. So to give you an idea of sort of where the complexity comes from and why it may be related to geographical applications, let's look at this example. So here I have several points and these white dots. And I want to ask a query, is it true that all these 4 points are collinear? Is it true that they lie on a line? So how we do that in a logical language? In a logical language, I would say that y points lie on a line if there exist numbers a and b, so that if x and y are the coordinates of a point on a line, then y equals ax plus b. Because we know that ax plus b defines a line on a plane. So now the problem is that these numbers a and b cannot be found in the database itself. I mean, there is no reason why this should be there. So basically, before, when I said there exists something, I always refer to things I had in the database. Now when I say there exists something, I refer to things out there that are not in the database. And so in this new type of databases, so the queries basically now can talk about infinitely many things. Not just a finite number of things I have in the database, but infinitely many things that are not in the database. For example, coordinates of points. And this really changes everything, right? So there was a theory on which he also worked close to a decade, and it brought together the key techniques from different subjects, from subjects such as model theory, algebraic geometry, and topology, particularly what's called tame topology, to databases, and provided really an unusual interplay between classical mathematics and database questions. So now I'll talk about the third application, and I'll switch gears. So the third application will not be about query languages for database. It will be about database design. So suppose we have a very small database and talks about courses, professors who teach those courses, and times when those courses are taught, right? Say I teach databases at the course databases twice, at Tuesdays at 11 and Thursdays at 10. And some other course, maybe Wenfei, a colleague of mine, teaches XML at Friday at 10 o'clock, right? So this database satisfies some conditions. So first of all, is it course determines professor? So if I know the course, I know who the professor is, right? So we don't have the situation when two people teach the same course. So two is that if you know professor and time, then this determines the course. As much as we want to be sometimes, especially close to a deadline, to have the ability to split into two different people doing two different tasks, unfortunately in real life we cannot do that. And I know that if I have to be somewhere on Tuesday at 11 a.m., it better be that database course and nothing else. Right? So, but the moment you have this very natural database that stores information that we want to store in a database, we start having some problems. And the problem is that it's hard to update information. Let's assume that Wenfei says that he doesn't want to teach XML anymore. And we say, OK, fine, delete the information that Wenfei teaches XML. But then we'll also delete information that XML is taught, the course XML is taught at Friday at 10 a.m. because we'll have to delete the entire record. Right? So there's no way to keep that without, to delete association between Wenfei and the course without deleting association between him and the course and being taught at Friday at 10. Or suppose that Flores, another colleague, says that he wants to teach advanced databases, but the time is not yet known. Right? So in this case, we cannot add that to the database because if you try to add advanced database in Flores, what do we put here? We don't know the time. So we have to wait until the time is known before we can add things. So how do we deal with that? Well, we deal with that by splitting the table into two. So the first table will have course and professor. And the second table will have course and time. So here we just say that who teaches what. And here we say at what times the courses are taught. So basically what we do, we store related concepts together. So the old problems disappear. So suppose that Flores wants to teach advanced databases. Well, now we can let him do that. We simply put it here. We don't need to know the time for advanced databases yet because we just store it in one relation. Or if Wenfei says that he doesn't want to teach XML anymore, then we delete the record from here, but we still have the record in the other relation that XML is taught at 10 o'clock. So, but unfortunately, new problems appear, and these new problems are more serious than the ones that disappeared. And the new problems that appear is that we can no longer enforce the consistency of the database. We can no longer enforce that professor and time together determine the course, because now professor and time are split over two different tables. And there's no way that I look at my database and I can enforce by looking at just one table that professor and course. Professor and time enforce the course. By splitting this concept over two different relations, I lost my ability to enforce consistency. And consistency is important. You don't want to deal with inconsistent databases. Right? It's a huge problem. I mean, unfortunately, every now and then we have to, but every time we have to, we recognize it's a huge problem. Right? So what do? So basically, we have design problems here. And the first design problem was the redundancy problem. That was the redundancy problem that led to the fact that we could not update the database properly. Right? For example, we had to store the facts that some courses are taught by some professors twice. But the problem with the second design is worse. It's potential inconsistency. And the question is, can we both eliminate redundancies in databases and enforce consistency? So the answer, which was already known in the 1970s, is no, we cannot. Right? So now the question is, what can we do? So we have design choices. One design choice is complete elimination of redundancies, like we did in this design with two relations. So when we have two relations, we eliminate redundancies altogether, so it's fine. Unfortunately, we lose consistency. So this design is actually very well known. It's taught in an absolute majority of database courses, something known as BCNF. But the original design that we had is also something that's taught in all database courses, known as 3NF. Actually, it's a design that may have redundancies, but guarantees consistency. And this happens to be the design choice of industry. Like you take something like, for example, I just looked at Oracle, which is one of the major database vendors, has database design FAQ. And if you just look at that, it just says achieve 3NF and then stop. And says, yeah, no, there are other forms, but they are for textbooks, not for real life. Okay? So, but then why is it good if it allows redundancies? Well, so if we'll continue with that, so basically what do we want to do with design? We want to achieve consistency, right? So consistency is a must. We don't want to deal with an inconsistent database, right? So once this is achieved, we try to eliminate those redundancies that you can. And this normal for this particular design choice just seems to be the best. And all database stacks and all practical designers, they can explain to you why. So you just talk to them and they explain to you why. But the more hand-waving they use, the more convincing the explanation is. So you hear an explanation and say, OK, and now you do the same explanation with your hands like that, right? And you're suddenly much less convinced, right? And then you can say, oh, and now the same explanation, but now I close my eyes. And then you're not convinced at all. So now the question is, can we actually give a proper explanation? Well, so what we try to do, we try to come up with a completely new approach to deciding which database designs are good, which are bad. So the idea was to measure redundancy or information content in a database. And there is a way how you can measure information. You use information theory, which is a branch of mathematics which was developed by Claude Shannon in the 1950s, and it deals with quantification of information. So the key measure that is used there is a measure of entropy. So the minimum entropy means that there is no information conveyed by some data. So it's completely redundant. Maximum entropy means that there is no redundancy whatsoever. So the way they did it, just to give you a very high-level overview, so we looked at the database, so here's a database, and we look at each cell in this database, and we try to measure amount of information in each of those cells, right? And the best designs are those in which this amount is the maximum possible. And of course, we measure it as some kind of entropy. So just to give a very small example, well, suppose we have a database like here with just 2 rows, 1, 2, 3, and 1, 2, 4. And suppose that we know that there is a requirement that we know the value of A, then we know the value of B. And now, let's say I look at this yellow 2 down here. Suppose I lose this value of 2, this yellow 2. Well, then I know what I have to put back, because I said that since A implies B, since A gives me the value of B, I say since I already have seen 1 here, and I know that whenever A is 1, then B has to be 2. Then even if I lose this value, I know it will be 2. So there's absolutely no information conveyed by this item. So the entropy of that is minimum. On the other hand, if I suddenly lose this value, say 4 of attribute C, there is nothing I would know about what I can put back. Right? So the entropy here is maximum because I can put anything I want. So if you just do that, then what you can actually prove formally is that this normal form, this design principle that has been choice of industry now for 30 years, is in fact the best that you can get. So in fact, what you can formally prove that the entropy with this principle will be maximum possible among all the designs that guarantee consistency. So in other words, if you need consistency, and we do, you cannot do better than that design principle that people came up with and used good amount of hand-waving to justify. But you can justify it by properly proving it, no hand-waving necessary, and you can say, this is really the best that you can do. Don't try to look for anything better, because there's nothing. OK, so I'll try to wrap up by going back to something that I left out before on the theory versus practice scenarios, having given you one and having promised to talk a bit more about it. And so as I said, there are 2 kinds of theory practice scenarios. So one is when we go from practice to theory, and this is more or less what I was showing you here. So when you sort of have this imaginary dialogue when practitioner says, I try to do better, but somehow I cannot, why? And theoretician, after thinking, and now we know sometimes after thinking for quite a few years, says, aha, that's not because you're dumb, but simply because there is no better way, and here is a proof. Right? But it may take a decade. So then there's from theory to practice. So what often happens, the theoretician, without anyone asking, says, aha, and shows a beautiful theorem. OK? Happens to all of us. So what happens most of the time in those cases? You sort of have this stone-faced practitioner standing there completely silent and puzzled. Sometimes it continues, but sometimes after thinking for a few years, could also be a decade, the practitioner says, hey, that's what we needed. Right? Doesn't guarantee to be that. Incidentally, we do quite a few, in my group, we do quite a few of this theory to practice theory. So we do it with things like connection with new data models, in particular XML and graph data, because many problems that in the world of traditional relational databases, those tables that I showed you, are nice and easy, become very hard for these models. And what you really have to do, you have to draw the boundary between what you can do efficiently and what you cannot do efficiently, right? In pretty much all the all types of problems. But so if we have this seemingly have this potential conflicts between theory and practice, do we actually need each other? And the answer is yes, of course we do. So as a great example, take relational databases. It was a neat theoretical idea proposed by Cod 40 years ago, now more than 40 years ago, that resulted in $20 billion a year business. But do we admit that we need each other? Well, not often, right? So what you would often hear from practitioners say, hey, I mean, again, I have these pesky theoreticians who keep telling me that, you know, in those circumstances that almost certainly will not occur, my algorithm won't work, right? Why should I care, right? And then I have theoreticians saying, I keep shouting that this algorithm is wrong, right? And they don't pay attention. It really happens all the time, right? But still, on the other hand, when you look at theory and practice together, so it's they survive together, they live together quite well. So if again, as an example, I will take the field of data management. So in the field of data management, we have two top conferences. One called SIGMOD that mostly deals with systems, and one called PODS, that Principles of Database Systems, that mostly deals with theory. So first of all, for the last 20 years, this conference have been held together. And absolutely everybody is very happy with the arrangement because it really helps both of them. And so I did like this little not very scientific experiments by looking at the most cited papers from PODS and looking at who cites them. And actually it turns out that the number of citations is roughly equally split between SIGMOD type of papers, System C papers, and theoretical papers, which is the way it should be. It's absolutely normal. So if you do basic research, right, and you do something that has an impact, it has to have an impact on both theory and practice in probably equal terms. And that's what's happening. So the bottom line, it's like every happy marriage. I mean, yeah, we quarrel sometimes. It's natural, right? But you know, sometimes in a visible way. But we still can't live without each other. Because practitioners need theoretical results. And theoreticians are motivated in our work by practical problems. Well, of course, what's slightly different here from the usual marriage is that I presented the thing as black and white, theory practice, right? In fact, it's all a shadow of gray, right? Because you can hardly find somebody who only publishes in SIGMOD or only publishes in PODS. We all, every now and then, we sort of stray to the other side a little bit, right? But still, it's true that, it is true that practice needs theoretical results, and theoreticians are motivated by those practical problems. And rather than leave you with that as a final slide, so I think it would be better to convey it by means of a picture. So, well, theoreticians would be happy if they could be like this little beaver who is happily looking at what seems to be the Hoover of Boulder Dam and say, I didn't actually build it, but it is based on one of my designs, right? And we love to say that. And theoreticians have to listen to us, because if they don't, you know, we know what happens, right? So they'd better listen. Okay, so to completely wrap up, so big thanks to lots of people. I want to especially mention my students and postdocs, because it's a great thing, especially for somebody who spent many years in research labs, to be in academia and to work with students and postdocs, whom quite a few are here in the room. Colleagues, everyone here at Informatics and LFCS, and lots of wonderful people over the world. So some of the results that I presented here, some sample results that I showed here, is joint work with 4 people. So the work on practical languages is joint work with Lim-Sun Wong and Michael Benedict, and the work on design is a joint work with Marcelo Arenas and Solmaz Kalahe. And that's it. Thank you.
So this being an inaugural, I actually have to give a vote of thanks before you get to ask questions. And I won't take too long, I hope. So thank you, Leonid. That was a wonderful talk, illuminating and intriguing in various points. The one quotation I sort of expected you to have there, and I think I'm not sure whether you exemplified it or whether you confounded it, is in theory, there's no difference between theory and practice, but in practice there is. And I think you gave arguments on both sides. So I thought one thing that Leonid did not stress there in his discussion of Moore's law and its effects was the fact that we see something similar in data. So internet backbone traffic rose by 64% annually compounded between 2006 and 2010. We currently, that is the world population, apparently, produce 1 gigabyte of data per head per month. So I think the sorts of questions you're talking about, Moore's law wouldn't help because the data's catching up anyway, and so it's clearly very important indeed. I also have to apologize on behalf of the principal who had intended to stay, but knew he had to leave before the lecture started. It wasn't because of the lecture, because he had to go down to the Scottish Parliament. We've had an election which has changed the political landscape, and I think he's gone to ensure we occupy the right place in it. So he's doing work for the university right now. And our head of school, Dave Robertson, also asked me to apologize. He would have liked to have been here, but he's in, I think, Hong Kong right now, again, on university business. So with that done, I thought that was a fantastic lecture. I learned things. I found it entertaining and enthralling. Does anyone have any questions? Not a one?
So, Leonid, what happens if you... you kind of laid out the landscape of theoretical possibilities. I'm wondering what happens if you relax the necessity of having an exact solution a little bit. So, and what happens if I say, well, my answer will be 99% correct, and I know I can't get that 100%, but if I can accept 99%, can I do something practical here?
Yeah, this is a great question, actually. And as a matter of fact, yes, there's lots of work on that. So first of all, there's all this work on approximation algorithms, right? And you both try to find approximation algorithms for things that when they work, and sometimes prove hardness of approximation. But what we actually do and we do quite a bit of that. And what happens quite often is that the problem that, indeed, as you said, that the problem that you cannot solve very precisely becomes a lot easier, right? If you say that you can tolerate a certain amount of error, right? So sometimes it's somewhat non-trivial actually to quantify that amount of error, right? Like in particular in this work on normalization on database design that I actually mentioned. So one of the reasons for doing that, as a matter of fact, so obviously I couldn't present all the details in the talk, was precisely so that we could quantify the amount of error and say how wrong can it be, right? Is this design of a database more wrong than the other design, right? Is this one better? So and the previous hand waving approaches would not let you do that. But that sort of things, I mean, we do all the time. I mean, the thing is that every now and then, even if you allow yourself quite bits of freedom in terms of how you relax the problem, because sometimes they still remain hard. Sometimes they still remain computationally hard, or they may remain undecidable, so that happens. But when I say problem, I don't mean like problem only with the exact solution. I mean, yes, so there is, for each problem, you try to do the exact solution, you try to see how it works. Then if it doesn't work, you try an approximate solution, you try to see if it works, right? Then you'll relax that. So the problem includes both exact and approximate solutions.
Hi, Bob's question was about one thing that engineers do, which is change the question. The other thing that they can do is change the paradigm. So I was wondering, on the near future in the horizon, we've got quantum computing coming up. How do you see that affecting theoretical computer science?
Nice. So I just attended a talk by Ella, actually this afternoon, on parts of that. And Alan presented a very nice picture of a physical experiment occupying a room about half size of this, doing something on 4 qubits, I think. No, it's a very good question, but do we have, and I think that the big task there is in 2 years to talk about 6 qubits. So we'll see how it goes, but I think Alan will be in a much better position than me to give you, at least she will give you a much more educated guess than mine on how fast that area will progress.
So you mentioned this wonderful phenomenon where a theoretician just does something, and then much later a practitioner goes, oh, that's exactly what I need. And you also mentioned the lovely example with COD just coming up with this nice theory of databases that then launched a 20 billion business. But that wasn't an example, right? COD knew that he was codifying this practical problem. What's your favorite examples of a theoretician just does something and much later it turns out to be valuable in practice, either from databases or elsewhere?
Well, I'm not actually so sure that I would agree, given the history, that that's precisely what happened with COD. I mean, so at that point, there were quite a few potential approaches to databases, and it was not clear. And in fact, what we heard at last year at Sigma, there was, 2 years ago at Sigma PODS, there was a session for the 40th anniversary of the relational model. And it's clear that absolute majority of people at the time viewed it as a pure theoretical exercise. So, as a matter of fact, there is this great article that a colleague sent to me, and this is an article of somebody who is looking at 4 very famous papers, including CODs, that led to Turing Awards, and trying to write reviews for those papers as if they were submitted to a conference now, and of course coming up with a strong reject for all 4 cases, right? And the main criticism of COD's paper was actually, this is pure theory. I mean, come on, so if you need some data in database, do you expect me to do all the joins all the time? It's completely impractical, right? So no, actually, I would have to think about that, but I would actually disagree with that characterization of COD's paper as something that was done to solve a particular practical problem.
So thank you, Leonid. I wasn't in the business when COD wrote his first paper, but I was in it soon afterwards. And I remember the sort of aftermath in which there were practitioners sitting around saying, oh, this is a delightful theoretical model, but it'll never work. And the interesting thing is that actually there weren't any theorems in COD's original paper. He just exposed it essentially as, nothing that we would class as a theorem, though it was just a very nice idea. And the interesting thing is that it didn't survive because of its theorems, but because very clever practitioners actually made it work fast, and work faster than all the other systems that were going around. And it turned out to be much more flexible. But this brings up, I think, something that I think theoreticians should also think about, not just about proving that things will stand up or fall down, or telling the practitioners that they're doing things the right way or the wrong way, but actually generating new models. That is to say, practitioners often come to you with rather vague ideas of what they're trying to do, and they rely on people like us to crystallize them, not to prove that they're right or wrong, but actually to give them a framework in which to think a bit better. And I just wanted to say that we should remember this as well. I'm sorry, that's a statement, not a question. But
no, but you're absolutely right. I mean, there are lots of examples of that. And another great example, of course, is the field of verification, right? Where, it sort of required the vision of somebody like Pnoeli to propose to write specifications in temporal logic, right? But incidentally, COD actually, so I'm not sure if it was the first paper or it was when exactly it was, so I would have to look at those papers from 40 plus years ago. But of course, what was done in COD, there was a theorem. And the theorem was that for first order logic, which is relational, what we call now relational calculus, which is declarative language, there is a procedural implementation, which is relational algebra. And that was a key contribution because it really separated declarative from procedural. And what all the smart engineers did after that, they took the procedural language and they showed that the procedural language can be implemented very efficiently, right? Using lots of other techniques, for example, like B-trees. Right? Yes, yeah. Yeah.
I'm now going to give the microphone to the last questioner, because after that we have something else to do.
So you started your very nice talk with this statement that sometimes you don't have enough time to be able to solve a problem. But when Netflix is giving out movie recommendations, they can't say, oh, sorry, error 503. They just scrabble together and put together the best thing they can in the time available. And so they famously fall back to dumber and dumber systems. So this is something that I know in my area we're very interested in, but I don't know what theory does. Do you know how to behave optimally given a harsh time constraint to sort of do the best as possible, and even if you include the computer time that you spend deciding what to do?
Right. Okay. So first of all, I mean, so we are talking about two time constraints, right? There's a time constraint on how long it will take to solve the problem. Then there's a second thing, which is time constraint on how long it will take us to prove that this is a time constraint to solve that problem, right? And there are plenty of examples of the second type of time constraint, like say P versus NP, that probably the time limit will be many dozens of years. So what we do, I mean, with this research, I mean, what we quite often try to do, and again, it takes several years, we just try to outline the boundary of what's doable, what's not doable, and then of course, if you know that something is not doable, then we try to find some other approaches, like approximation, as was already mentioned, is one of them. But it's definitely nothing that we are doing sort of, in real time, producing all the theoretical results. Oh, yeah, you have this problem. Okay, 15 minutes later, yeah, here's the proof. No, it's nothing like that, right? And it can easily take a decade. And if you just say that this is hard to solve, then what we have to do, we have to look at approximate solution, we have to look at ways around, and we have to look at different models, we have to look at substituting the questions sometimes, there are lots of techniques.
Okay, so what we're going to do now is not to stop the questioning, but to stop the single-threadedness of the questioning by taking it next door where there's also some lubrication of various sorts, I hope. So you can keep asking Leonid and each other interesting questions. Thank you very much, Leonid. Fantastic talk.
This production is copyright the University of Edinburgh.